Welcome to video section 3.8, implicit differentiation. So far in this chapter we've been considering the derivatives of functions, okay? But we're going to look at how to find a derivative of something that can have an equation but is not necessarily a function. And so this first special case we're going to consider is a circle. So what you see off to the right is the circle that's given by the equation x squared plus y squared equals 25. You may remember that a circle is given by the general equation when it's centered at the origin. General equation x squared plus y squared equals the radius squared. And the reason for that is just a simple Pythagorean theorem. If you pick any point on the circle and you look at its coordinates x and y, right, you kind of go over some distance x and go up some distance y, and then you were to draw the radius in there. Of course, you have a right triangle right there, and it satisfies the Pythagorean theorem. X squared plus y squared is r squared. In this particular case, we have r equal to 5, radius of 5, and so that's where we get our equation. So the question is, what is the slope of the tangent line at the point 4, 3? If we look at our graph, I'm close to it, but anyway, right about here is the point 4, 3, and it would have a tangent line, and I'm going to try and draw that in. Let me erase those things first. Okay, so drawing that tangent line in, it's going to be something like that. It's not maybe the best drawing ever, but you can see how there would have a tangent line with a negative slope. So in the past, we would have needed to find an explicit equation to find the derivative, meaning we would have had to solve this equation, x squared plus y squared equals 25, do some steps, and get down here to y equals something. And you could see that if you did that, what would happen is you'd have to subtract x squared from both sides. You get 25 minus x squared, and then take the square root. The problem with that, it's not a true equation unless we eliminate one of these. I'm sorry, it's not a true function unless we eliminate either the plus or the minus, because it fails the vertical line test. So we would have to maybe just consider the top half of it. So we want to avoid having to solve an equation as a function and consider it in multiple parts. Instead, we just want to take the derivative of the equation as is. So how are we going to do that? Well, it's something called implicit differentiation. And here are some steps and ideas about it. So here it reads, to perform implicit differentiation on an equation that defines a function y implicitly meaning not explicitly, it's not just solved for y, it just has y somewhere in the equation, in terms of the variable x, use the following steps. So number 1, take the derivative of both sides of the equation, kind of like an algebra idea. What you do to one side, you do to the other. Keep in mind that y is a function of x. That means we'll be using the chain rule, and we're going to use Leibniz notation when necessary. So that's that dy dx kind of notation. Rewrite the equation. Step 2, rewrite the equation so that all terms containing dy dx are on the left. It could be the right, by the way, as well. So it doesn't have to be on the left, because it's true that if x equals 2, then of course 2 equals x. But this one is just basically saying to separate the variables. Okay, and then number 3, factor out dy dx on the left and divide it so to isolate it. So let me give you just an example from the one that we're looking at with that circle. So what you want to do to this equation is take the derivative of both sides of the equation. So we're going to take the derivative with respect to x of the left-hand side of x squared plus y squared, and also take the derivative with respect to x of the right-hand side. That's just 25. Let's do the easier side first. Of course, we might remember the derivative of a constant, so 25 would just be 0. That's easy enough. Now the derivative of x squared, this first term right here, with respect to x, would just be using the power rule, 2x. But when we take the derivative of the y squared term, the only thing different is we have to remember that y is a function of x. And so you might imagine that that term, I'm going to write it off to the right over here, y squared is acting for us a little bit like there's some function. Of course, I'm going to put it in air quotes. Right? There's some function y that's embedded inside a function that's being squared. So we have to treat it like it's, well, it is the chain rule, where we can use the power rule on y squared, but then we have to multiply by the derivative of what's inside. And we're going to use this notation that we mentioned above, and here's how we do it. So as we take the derivative of the y squared term, we're just going to say that's 2y, that's using the power rule, but y itself is a function, so we're going to multiply that by the derivative of y with respect to x. That's dy dx. Okay, so now steps 2 and 3 are basically get dy dx by itself, because dy dx is the derivative. So the next step would be to subtract 2x from both sides of this equation. And let me bring that up here on the right hand side. Now it reads something like this: 2y dy dx equals negative 2x. Then we will divide both sides of this equation by 2y, and we can have our derivative dy dx. Let's notice that the 2's simplify, so I'll just write that as negative x over y as our derivative there. Let's go ahead and go back up to the top to entertain what I was asking earlier, which is what would be the slope of the tangent line at the point 4, 3. That was that question originally there. You can see it's that negative slope line off to the right. Well, if you have the derivative, which we did here in example 1, as negative x over y, if you wanted the slope of the tangent line at the point 4, 3, you're just going to use the derivative that we found. Notice that the derivative is expressed in terms of both the variable x and y, so we're going to use the negative x. The x is 4 over y, and the y value is 3 at that particular point. And so our slope of our tangent line would be negative 4/3. That's how that's done. Let's look at a little more complex equation. This one has quite a few terms. So we're asked to find the derivative dy dx, but not at any particular point. So the steps are: step 1, take the derivative of both sides of this equation. So you can think of this whole side of this left side, the whole side of the right. We're going to take the derivative with respect to x, because it asks us here to. If we have something like dy dt, that would be with respect to t or whatever. Just be careful of the variable. And so we are going to take the derivative with respect to x of 3x squared minus 5x plus 12 on the left-hand side, and something similar on the right-hand side. On the right-hand side, we're going to be considering the chain rule because we have it in terms of y. But the left-hand side, since it's with respect to x, and all of these terms are in x, we can just use the power rule. So that would be 6x minus 5. Of course, the derivative of 12 is nothing, or 0. On the right-hand side, using the power rule with the chain rule, the derivative of 5y squared, bring the power down. It's 10y, but then multiplying by the derivative of y in terms of x is dy dx. Also in this term, using the linear or power rule, the derivative is 4, but we have the derivative of a y, that's dy dx. This term is just a 1, a constant, so that's just a 0. This time, notice we have two terms with dy dx. Now, up in my steps here above that I got from the book, it said rewrite the equation so that all the terms of dy dx are on the left, but this time I'm going to do the right, and the reason is, well, they're already on the right. Why work too hard? And so let's factor out dy dx on the right hand side from each term. We'd have 10y plus 4. That way we're rewriting the expression where we only have one dy dx floating around. And then the last step is divide by that expression by 10y plus 4 on both sides, and you will have it. And so let's rewrite this final answer. The derivative dy dx is equal to the expression that we ended up with over here after simplification. And there's no more simplification than this, 6x minus 5 over 10y plus 4. So if you wanted to use this derivative, it looks the same in the sense that you have x and y in the answer, so you would need to plug in the entire point x comma y. You can't just plug in an x value in this particular kind of derivative. That's all for that example, though, because we're not asked to find the derivative at any point. Go ahead and try example 3, and pause the video and come back and see how you did. Okay, you probably noticed this was something a little bit different, and maybe you didn't. I hope you did. There's the chain rule here. We have x squared times y, so we have, not the chain rule, say that again, the product rule. You have x squared times y, and so let's remind ourselves of the product rule. The product rule is that if you have the derivative of any two functions multiplied together, I'm just going to abbreviate f times g. It's the derivative of the first times the second plus the first times the derivative of the second. F prime g plus fg prime. So in this case, x squared will act as f and y will act as g. So let's go ahead and get into the derivative. All right, so we're going to take the derivative of this left-hand side. I'm just going to write my d over dx right in there. I'm going to take the derivative of the right-hand side. I'm going to write my d over dx right in there. So this will be the product rule. Derivative of the first, derivative of x squared is 2x times the second, y. That's the first part of the product rule, plus the first function, just as x squared, times the derivative of the second, times the derivative of y. The derivative of y is just 1 dy dx. The derivative of y, 1 dy dx. On the right hand side, again, the derivative of y is 1 dy dx, and the derivative of negative 7, that's a constant, is 0. This time we have dy dx on both sides, and so you want to get those on the same side. You can do this in a variety of ways, but I'm going to go ahead and once again put everything to the right hand side. I'm going to subtract x squared dy dx from both sides, and that will eliminate that term. Let's rewrite what we have here. Now on the left, all we have is 2xy, and on the right side we have dy dx, and now I'm subtracting an x squared dy dx. Notice that we have dy dx on the same side, so we're good to factor that out now. Don't forget that dy dx times 1 will give you dy dx, and then this term will have a minus x squared. All right, and lastly, we'll divide each side of this equation by 1 minus x squared, and I have it. Okay, so that will simplify out. So our best answer here, our derivative, dy dx, is 2xy. You don't have to write the parentheses, but you can, over 1 minus x squared. All right, again, if you had a particular point, hopefully that's what you got. A particular point, you would plug in x and y. Number 4, example 4, find all points on the graph of this equation at which the tangent line is vertical. Okay, so there's some words we have to think about here. A vertical tangent line is a tangent line that's straight up and down. That would be an undefined slope. Another way to think of it is it's all rise and no run, right? That's when your slope formula, when you would have some y value, you'd have some rise, but your run would be 0. And that's undefined, of course. You can't divide by 0. So that's kind of what we're looking for. So the way that we're going to do that is if we're considering the slope, right, the tangent line, that's the derivative piece right there. So we need the derivative of this equation, and you see that we're going to have to use implicit differentiation. Again, I'm going to kind of cheat the first step here a little bit by just squeezing in both sides. I'm going to do a derivative with respect to x, and let's go ahead and do that. All right, so the first term, y cubed, let's use the power rule. That's 3y squared, Leibniz notation, considering y as a function, times dy dx. And then the second term, the derivative of 27y is just 27, again, dy dx, because we're differentiating with respect to x and on the y there. The right side a little bit easier because we're differentiating with respect to x. It's just x squared. Use the power rule. It's 2x. The derivative of negative 90 is 0. So let's get dy dx by itself. By factoring out, we have 3y squared minus 27 is 2x. And dividing both sides, I won't write in the step, but you can see it, 2x divided by 3y squared minus 27. Now let's go back and answer the question because that's our derivative. We were asked to consider where is the slope undefined or vertical. It said vertical, but it meaning undefined. That would be when our denominator, vertical when denominator equals 0. All right, so in this case our denominator is 3y squared minus 27. We want to consider when is that equal to 0. Let's add 27 to both sides of this equation. We'll be here. Divide both sides by 3. We'll be here. And then take the square root. We'll have plus or minus 3. So those would be places on the graph where the tangent line is vertical. But it does say, notice it says find all points. That is not exactly a point, that's a value. So those are y values, right? These are values. If we're going to find points, you have to go ahead and plug those y values into the original equation to figure out exactly what those points are. Let me give myself a little bit of room here. Maybe on the notes you can squeeze that in there as well. So going back to this original equation up here, let me just highlight that so you know what I'm talking about. So what we're going to do is plug into that equation the values that we were given and see what those points would be. Since we have two values, plus or minus 3, let's do them one at a time. Okay, so if y is 3, let's see what happens when we plug into that equation. We get 3 cubed minus 27 times 3 equals x squared minus 90. 3 cubed is 27. 27 times 3 is 81. So 27 minus 81 is negative 54. When we add 90 to both sides of this, we get 36 is x squared. And then if we take the square root of both sides, that step there, right? Don't forget your plus minus. We get plus minus 6. Okay, so that tells us our first 2 points is that when y is 3, the x values are 6 and negative 6. I'm going to make a list of the points over here on the very right-hand side. I kind of got to squeeze this in. Let me see if I have room, right? So when y was 3, that was our thing, then x is 6 or negative 6. So we're going to write 6, comma 3, and negative 6, comma 3 Again, make sure the order is correct, right? That was when y is 3, x can be either of those values. Let's also consider back here to our original solution, when y would be equal to negative 3, what would happen? So when y is negative 3, and you might pause the video and try that yourself, see what happens. So you're going to get negative 3 cubed minus 27 times negative 3 equals x squared minus 90. Here you're going to have negative 27 plus 81. This time I believe you get 54. It's x squared minus 90. Adding 90 to both sides, you get 144. And so here we learned x is plus or minus 12. So to finalize our answer here, when y is negative 3, x could be either of these. So our other 2 points would be 12, comma negative 3, and negative 12, comma negative 3. Those would be all of the 4 points where the where the tangent line is vertical. I thought it might be useful to give you a visual of this. This kind of equation, of course, is not something that any of us know how to graph off the top of our heads. And so I used Desmos to graph, and it has this really interesting shape. You can see it's not a function because it curves back on itself, but it is an equation. And I then labeled the 4 points that we found algebraically. And maybe you can kind of see it in your head already. I don't know if you can or cannot, so maybe I'll draw one in. But if, like, you take this example of negative 6, 3, if you think about the line x equals negative 6, you can see, let me just change the color so it's not the same color as the function. Let's go orange. You can see how it is a perfectly vertical tangent line to at the point negative 6, 3. In fact, all of these points would have a vertical tangent line. So we were able to figure that out algebraically without having a visual of a graph. So kind of cool. Let us proceed in the section. So here we have the topic finding tangent lines implicitly. So implicitly is the method we're using, implicit differentiation. So now that we've seen this technique, we can apply it to the problem of finding equations of tangent lines. That's something we've done again and again and again using y minus y1 equals m times x minus x1. So example 5, using the circle from before, x squared plus y squared equals 25, find the equation of the tangent line to the curve when x equals 3. Now you can scroll back up and figure that out, but let's not redo the whole problem. Remember we had that dy dx was equal to negative x over y. We're going to use that. The problem, of course, is that we only have the value when x equals 3, but our derivative requires us to have x and y, right? So we have to have both. So if you're only given information when x is 3, then you have to go to the trouble of plugging in x is 3 to see what happens. Let's go ahead and do that. So 3 squared is 9. If you subtract 9 from both sides, you get 16, and you'll figure out that y is plus or minus 4 after you take the square root. And so you really have 2 points to consider, right? The first one is when x is 3, right, y could be 4, and the second one is when x is 3, y can be negative 4. Let me not put points, but point, right? The other one is when x is 3, y is negative 4. So I have 2 different points, and you can think of graphically, right? There's this circle with the radius 5. One of the points is over 3 and up 4, maybe right there. And the next one is over 3 and down 4, right over there. We're going to have a tangent line here. We're going to have a tangent line there. You can see one has a positive slope and one has a negative slope. And so we're going to find the equation of the tangent line of each, right? We're going to actually find the equation of that actual line. Let's go ahead and start with this first one, which is at the point 3, 4. All right, so at 3, 4, our derivative value, we're just going to use our derivative from over here, is the negative x value over the y value, negative 3/4. All right, so we have all the details we need. Y minus y1 equals m, that's our slope given by the derivative, is equal to x minus x1. There is an equation of our tangent line. If you wanted to distribute, you can get more. Like go into slope-intercept form. Let's do that. Negative 3/4 times x is negative 3/4 x. When you distribute negative 3/4 times negative 3, you get, let's see, 9/4 would be a value there. Then you're going to add 4 to both sides right here. And when you add 4, that's the same as adding 16/4. And so that looks like that's going to be 25/4. So that would be the equation of that line. And then let's take a look at the bottom line. You can see it looks like it's pretty symmetrical, so we're going to probably see some similarities in the derivative. And so let's do that. Our derivative, again, will be equal to the negative x value, and this time we have negative 3 over a negative. So we have a negative over negative, turns us back to a positive slope. And you can tell by looking at the picture over here that that does have a positive slope. So let's plug in y minus y1 equals m, so 3, x minus x1, and so we'll get 3/4 x. Again, when you distribute, we're going to get that 9/4. In this case, it's going to be a negative 9/4 because we don't have a negative slope. So I'm doing a little bit of work off to the side. We have a negative 9/4. And then on the left-hand side, that's going to be a plus 4. So we're going to be subtracting 4 from both sides. And so we'll end up with a negative 25/4. All right, so a lot of symmetry there. And that is the equation of our line for the bottom one. So they have just oppositely signed slopes, and then they have opposite y-intercepts. So that's how you would find the equation of the tangent line. Plug in both the values to find the derivative and just use as before. All right, this is one for you to try right here. Find the second derivative for the circle x squared plus y squared is 25. Why don't you pause the video and see what you can figure out? Okay, hopefully you've tried that. And so let's pick up where we would have been at from the previous point. We already found this derivative. We found the derivative of this to be negative x over y. So if you want the second derivative, we remember from before, that just means take the derivative of the derivative. Great, let's do that. So the second derivative, we're going to look at the derivative we already have. Now this is actually a quotient. So we want to use the quotient rule or rewrite it where we can use the product rule. But I'm going to go ahead and use the quotient rule because it looks like one already. You might remember that the derivative, hopefully you have this memorized, of a function divided by a function is equal to f prime g minus f g prime over g squared. That's something we have committed to memory hopefully at this point. Let's utilize that for this particular problem. Okay, so f prime, derivative of the top. The derivative of x is negative 1 times the bottom, y, minus just the top, negative x. Again, I'm treating the top as the negative there, so I'm carefully assigning the negative to the numerator, times the derivative of the bottom. The derivative of the bottom, derivative of y, we just write as dy dx, over the denominator squared. Let's clean this up quite a bit. So we got negative 1 times y, negative y. Here we have negative x. That'll act like a positive x, dy dx over y squared. Now, that's the second derivative, but you might notice that it looks funny because the second derivative has the first derivative buried in it. We probably don't want to do that. We want to substitute for that. You wouldn't want to say the second derivative equals blah, blah, blah plus the first derivative. You want it to just be pretty explicit what it is. So what do we substitute? Well, we already know what the first derivative is, so that's what we're going to substitute in. So we're just going to rewrite this as negative y plus x times, I don't think I need the parenthesis quite that wide, times the dy dx, which we already found to be negative x over y, all over y squared. And there you go, we have it. Now, of course, you could work with this in a bunch of ways and rearrange this algebraically so maybe it looks a little bit cleaner and neater. But if you're going to use the derivative, it's pretty safe just to leave it at that point and plug in as needed. So I'm just going to make a habit of that and just say, that's good enough. I don't see anything that obviously simplifies right off the bat. So let's move on to the next page. I want you to go ahead and try this one. This one has a lot to it. Go ahead and find the second derivative of this. Come back to the video and see how you did. Okay, I thought I would jump you in at this point. At this point, I've taken the implicit differentiation steps to find the first derivative, and now I'm ready to find my second derivative. And hopefully you got through this. Let's see what happens. Notice in our first derivative, we now have, it looks to be a quotient, so we're going to use that quotient rule once again. Okay, so the quotient rule says the derivative of the top, the numerator, that's going to be 6, times the bottom, 10y plus 4, minus just the top, 6x minus 5, times the derivative of the denominator, which would be 10 dy dx, all right, all over the denominator squared. And the only thing left to do would be to substitute this dy dx for the dy dx that we already had given before. So let's do that and then look for any obvious simplification. We have 6 10y plus 4 minus 6x minus 5 times 10 times 6x minus 5 over 10y plus 4 over 10y plus 4 quantity squared. Once again, if you were to simplify that, you got a lot of work to rearrange and do a lot of algebraic manipulation really just to make it look a little bit cleaner. I think that's unnecessary. That's fine for a second derivative because the point would be to use it. So I'll just leave my answer as that. Okay, so let's apply this to a problem, which is our last problem. It says, in a simple video game, a rocket travels in an elliptical orbit whose path is described by the equation 4x squared plus 25y squared equals 100. And you might remember how to work with ellipses from before, and you may or not, but an ellipse acts like an oval, right? So we have that going on. If you wanted to get a pretty good picture of this graph, then you can use a Desmos. The rocket can fire missiles along lines tangent to its path, right? So as the rocket's going around, let's say it's going around, right? Round and around and around. Let's say it gets right here at this point. If it were to fire a missile, it would come out as a tangent line like that. That's kind of what it's saying. To destroy an incoming asteroid. Like here's an asteroid over here. So the idea in this video game would be to explode that. And the asteroid says to destroy an incoming asteroid, travel along the positive x-axis towards 0, 0. So there's like some axis here, and this asteroid is just, you know, flying in this way towards the point 0, 0. That's what's going on in the video game. If the rocket fires a missile when it is located at 3, 8, 5, where will it intersect the x-axis? And so we're going to have to make an assumption here. So over 3, 1, 2, 3, and up 8/5. Let's just assume that point is about right there. All right. Now, if we were to look at its tangent line, let me erase this other tangent line. Oops, didn't mean to delete all of that. Then our tangent line will look something like this. So you can see that the asteroid isn't yet in its zone, but if we timed it correctly, maybe the asteroid would come in there. So, of course, the tangent line goes in both directions, but we want to know where it intersects the x-axis, so we're really interested in that. So we've got a lot going on here. So what we first need to do is figure out, okay, what is this tangent line? We need to figure that out. And let's go through the steps as before. To do that, we need a point. We have that, and we need the slope. We don't have that, but the derivative will give us that because it says in this problem that it is a tangent line. So I'm going to take the derivative of this equation. I'm going to do that implicitly. So let's do that over here. So derivative with respect to x of 4x squared plus 25y squared on the left, and the derivative with respect to x on the right as well. So here we will get 8x plus 2 times 25, 50y, don't forget your dy dx, equals derivative of 100 is 0. Right, if we subtract 8x from both sides, we get negative 8x, and then divide by 50y, we get that. It looks like you can simplify by dividing by, I don't know, 2 over 2. So we get negative 4 over 25y, negative 4x over 25y. That's a fine derivative answer. And since we want it at the point at 3, 8/5, let's plug in those values. So x is 3 and y is 8/5. It looks pretty crazy, but I see something nice. It looks like 5 goes into 25 5 times, and we get negative 12 over 5 times 8, 40. And I think we can divide these both by 4, and we get negative 3/10. So that's my m. That's my slope of that tangent line. Now I'm ready to write my equation. Y minus y1 equals mx minus x1. So let's write it y minus the y value of 8/5 equals m, the slope, negative 3/10. That was the point of doing all this work over here. X minus 3. And we want to know where it will intersect the x-axis. Now, you can save yourself a lot of trouble if you kind of translate what that means. On the x-axis, that's a special location because the y value is 0. Now the x value we don't know because that actually is the question. Where will it intersect the x-axis? But the key is to know that y is 0. So since we have this equation right here, what we're really interested in is when y equals 0. Great. Let's just plug in a 0 for my y. Okay, so when we do that, we get negative 8/5 equals, and let's go ahead and distribute here, negative 3/10 x, and then we get plus 9/10. And solving for x, I need a common denominator here. It seems I'm going to multiply this left side by 2 over 2, and I'll get negative 16/10. And then I'm going to subtract the negative, or excuse me, subtract 9/10 from both sides. So I'll write it as such. And then, since we have a common denominator now, negative 16 minus 9, negative 25/10 equals negative 3/10. Now, you can do this in 2 steps, but if you remember a little trick, you can do this in 1 step. And so the 1 step would be to multiply both sides by the reciprocal. Maybe you remember that. Hopefully you do. If not, there you go. That's kind of the trick. And the reason that works is because those simplify all out, and we're just left with x equals whatever this value is. So let's see, the 10 simplifies with the 10, negative times negative positive. Seems your answer would be x is 25/3. So that would be where it will intersect the x-axis. It would be at the point 25/3, comma 0. All right, that's it for this video. Hope to see you in class.